Hey everyone, this is Derek, and this video is about the definite integral. And definite integrals are when we start having these what's called limits of integration on the function. So we're going to be integrating it from some spot to some other spot. In the next section, we get pictures, and then this makes so much more sense. If I had some function f of x, what we're doing is we're finding the area under this curve when we do this integration. We don't know that until we get to the next section. So right now we're going to look at it as the fundamental theorem of calculus, which is really, this is the best way to do the calculation. It just makes a little bit more sense when I get to talk about this at the same time. So in this section, I'm going to kind of do more calculation, and in the next section we'll get a little bit more of what just happened to hopefully make it make a little bit better sense. That said, the math, if you can do an integral, the math on this is pretty straightforward. The integration is the hard part. What the fundamental theorem of calculus says is that if I take the integral of this and I get its antiderivative, and then I evaluate that antiderivative at these two values and take their difference, that's going to be the same thing as finding this integral. And again, what we're really doing when we're finding this integral from A to B is we're finding the area under a curve, as we'll see in the next section. Here I get to just plug in two numbers, subtract them, and then that's what's giving me that area under the curve. So that's going to be the power of integration, is it lets us find these areas. So let me show you what this looks like with an example, and it's really not that bad at all. For this first one, let's go, so we're going to integrate, and that's going to be 3x. This is squared, so 2 plus 1 would give us 3 over 3, and I'll clean all that up in a second. 6x to the 1 plus 1 would be 2 over 2 minus 2x to the 1 over 1. And now we say we're going to evaluate that from 0 to 2. If I were being better about my notation, I would have one of those at each step, and that's just really annoying, so I'm thinking of it kind of as one big thing. This cancels, and cleaning that up, I'm going to get x cubed minus 3x squared minus 2x, and that's from 0 to 2. And so this from 0 to 2 is just sort of a way to write this. This would mean the same thing as I'm going to find, now this is my f of x because it's my antiderivative. So now this is telling me to find f of 2 minus f of 0. So here we'll put in our 2. So that part is f of 2, and then we're going to subtract f of 0, which hopefully you can see 0 cubed minus 0 squared minus 2 times 0. It's all going to be just a big old 0 there on the end, so it's nice when that's a 0. So it'll just be whatever this is. So 8 minus 12 minus 4, so it looks like negative 8. And we'll get into what negative areas are, again, in that next video. So this one's the too easy it's hard. It's a nice one to talk about. Again, this is fundamental theorem of calculus. But if we think about what that would look like, if I'm up here at 9, I have a line that just is flat, goes, it's 9 forever, and I want to find the area under that from 0 to 8. Well, the area is going to be 72, right? Because it's 9 high and it's 8 wide, not drawing a scale, and 8 times 9 is 72. So if I do this integral, I'll get f of x will equal 9x to the first over 1, right? Evaluated on the interval from 0 to 8. So then that would be 9 times 8 minus 9 times 0, and there's the exact 72 minus 0 that we would expect. Okay, so for this one, this is cool, we can do this. So this is just going to be from 1 to 5, and then instead of writing that as a fraction, I'm going to switch that up to make it look more like a power. So just using my negative exponent to get where I can use my power rule. And then we'll go ahead and do our integration. So that's going to give us -2 plus 1 would be -1. So 4x to the -1 over -1. And that's going to be evaluated from 1 to 5. And then this is kind of ugly, so let me fix that up a little bit. This is going to be -4 over x evaluated from 1 to 5. So I'm just moving x to the -1 downstairs, and I don't like the negative in the denominator, so I'm just kind of putting it in the numerator. So this will be -4 over 5 minus, and then careful there, -4 over 1. And then here, we'll need a common denominator to add our fractions, so I'll just do 5 over 5. So that's going to be -4/5. Minus and a minus is going to change that to a plus. 4 times 5 is 20 over 5. So that looks like 16/5. So this one looks kind of like the same thing, except careful because it's that 1 over x. And so that's the one, remember, that gets us our natural log. Because if I try to bring that up, x to the -1 plus 1 division by 0. So for this one, we'll just think of this as 9. We're integrating from 1 to e of 1 over x dx. So that will be 9 times the natural log of the absolute value of x evaluated from 1 to e. And then doing that, we're going to get 9 times ln e, and then minus 9 times ln of 1. So 9 times ln e is a 1, so that's just a 9. ln 1, natural log of 1 is 0, so 9 times 0 would be 0, and so 9. Okay, so this is going to be kind of like a natural log one, but this is where we do have to take into a u substitution. So u equals x plus 4. And if I do that, -3 to 5, 1 over u, that looks good. So then du equals, right, that would just be a 1 dx, which is great because that's exactly what I have. So then integrating, we're going to have natural log of absolute value of x plus 4 evaluated from -3 to 5. So that will look like ln of 5 plus 4 would be 9, and then minus natural log of -3 plus 4 would be 1. But remember, natural log of 1 is 0. So this will be natural log of 9. Okay, so again, this feels like a u substitution because this is just kind of confusing looking. We want to go for the thing with the bigger power, so that's going to be that x squared down there. So we're going to let u equal 5x squared minus 3x, and now du equals 10x minus 3, which is perfect because that's exactly what we got. So then I can rewrite all that as integral from 1 to 2, all of that, oops, that should have a dx on there, sorry, is now du, and then this is just going to be a 1 over u, du. So that's going to be our natural log. So natural log of u evaluated from 1 to 2, which is the natural log of that stuff. And then plugging that in, I'll write out a big mess here and come back. Okay, so we have natural log. 2 squared would be 4 times 5 is 20 minus 6. And natural log 1 squared would be 1, so that's 5 minus 3. So natural log of 14 minus natural log of 2. And you gotta be a little careful there, those are both numbers. And we have that property that said if we have ln A minus ln B, I can write that as natural log of A over B, which means I'm going to be able to simplify. So ln of 14 over 2 is really the same thing as ln 7. So we want to make sure we get that into simplest form. Okay, and so then this last one, let's get the 9 out front, 0 to 4. E, we got this, this time I think I will just do the, let me do the shortcut this time. The last time I did this the long way. So here I'm just going to do, when I integrate this, I'm going to use that. So that will be 1 over, so if this is my k, then we do 1 over k e to the kx. So this will be 1 times 1 over negative 1/3 e to the negative 3x. And again, you can do that by the same u substitution I did, or you can do it by the integration formula. Canceling there, we're going to get negative 3e to the negative 3x evaluated from, I should have 0 to 4, 0 to 4. So I can write this a couple of ways. When I go to write this out, I could write that twice, or since I have this e to the negative 3x, I can kind of think of this negative 3 is factored out front. So I'd have e to the negative 3 times 4, and then that would be minus e to the negative 3 times 0. And so you can see I would have just had a negative 3 on both of those. So I'm just kind of factoring it out front. And so now that gives me negative 3, and then e to the negative 12. Anything, again, e to the 0, anything to 0 is 1, so that's a minus 1. And then that would be the form we want the answer.